This live presentation was produced in Ashland, Oregon by the Rogue Valley Metaphysical Library and Event Center. RVML relies on the support of our volunteers, members, and donors to organize and present these programs. For more information about this presentation, or to borrow, download, or purchase other recordings from our catalog, please visit our website at rvml.org.
A few minutes ago, Bruce was telling me that he was happy to see so many geometers walk into the room. And I said, oh yeah, that's kind of reminds me of when I first started teaching, and I basically got it because I was interested in geometry and I was breathing. So thank you for coming. We do have a lot of material to go over tonight. If you have any questions during my talk, I'd welcome that. I would like to ask a few questions of you. I'd like a little participation at times. For example, right now, I'd like to know, are any of you currently math teachers? Nope. Any of you currently homeschooling parents? Aha. Okay, just interested in universal mathematics? Good, okay. The reason I ask is because I am trying to get these materials in front of teachers. I, like most of us, was raised in a normal mathematics, normal school system, and I'm finding that the normal school system's doing a great job of turning a lot of people off, not just to mathematics, but to education in general. And as I've taught for the last 12 years now, internationally, I'm uncovering a lot of tremendous things in mathematics, and it's really surprising to me as I go through this work. Each year, as I revisit a topic, there's something more, then there's something more, and as I have a base, I discover even further things. That led me to giving workshops in this country and in Europe. That led me to writing a book about the things I'm doing, and these things are available on the back table if you'd like to know more afterwards. So without further ado, how about if we start? I'd like to ask you all a general question. How many of you enjoyed your mathematics experience in school? Okay, a couple people, good. I enjoyed mine. I was one of those guys that the other students in the class hated, because in grade school I was the best in the class. Always the one with my hand up first. High school, always the one with my hand up first. Other students hated that. A couple of years ago I had a student like that. I hated that. I kept wanting to throw something at him so that he let other people have a chance. And I must apologize karmically to all the people that were in my classroom with me, because I didn't let them have a chance. One of the things I've found teaching that's been a joy is evening the playing field. Normally I find that in class, just as here, about a third of you raised your hand to say that you enjoyed mathematics. That's my experience in school.
That's the question. I raised my hand.
What?
Do I enjoy mathematics? You asked, did I enjoy mathematics in school?
Okay. Then let me rephrase the question. How many people today enjoy mathematics?
Yeah.
Okay, a few more. Good. Sorry, thank you. Thanks for rephrasing the question. So I guess I should look at that with my students. What I would say is 1/3 are doing well in mathematics when they walk in my door. 1/3 tolerate it, do average work, and 1/3 are failing. What I've found is right away I even a playing field with the students, and by the end of 1 year or 2 years, usually I have them for 2 years, those failing students are not failing. They might be passing average. The average students are generally getting B's and A's. So this idea of a bell curve totally goes out the window. And the A students, the typical A student that we've got is somebody that can work quickly with numbers, work quickly with a calculator, and man, they think that's everything. And I'll give you an example. This guy that always had his hand up, I also teach physics, and I was trying to get the students to look at the physics, the possible physics of the human aura. I gave them lots of information about this, about crystals, how we could look at these things as scientists, and all this guy wanted to make was an electromagnetic rail gun. So this is the unfortunate reality that our best mathematicians that we're trying to encourage are building a technological future for us, full of technological weaponry and exciting toys with really no development of their own humanities. And that's something that I've been doing with my education process as well. So I'm going to give you a brief synopsis of some things I've discovered, and I hope that it's pretty exciting for you. I've got to say, though, the last time I presented this, actually 2 times ago, was a group of homeschooling parents, very general population. So when I walked around town today looking at Ashland and the people of Ashland, I realized, you're not in Kansas anymore. So thank you for coming tonight. I'm honored. This town looks great. As I walk around the streets of Ashland, it just seems amazing, the environment here. So I'm really excited to present here. The last group that I was presenting to was in Madison just this last weekend at a math conference. And I had 10 minutes to present almost the same amount of material, so I was speaking very rapidly. I don't know if I made sense or not, but I hope tonight that it'll make a lot more sense. Okay, what is geometry in mathematics, and why won't it go away? What I'd like you to do is answer this question. Realize this question came out of me teaching at a group of homeschooling parents. So I'm going to rephrase the question. I'd like to give you a moment to pause and think about an answer to this. The question originally was, to do a good job teaching my own children mathematics, I would like to. So how about if we rephrase that and say, to do a good job understanding mathematics, or for myself to understand mathematics, I would like to. I wonder if you could just pause for a moment and think about it. To understand mathematics, I would like to
kindle some interest.
Kindle some interest. Great.
That's where it starts.
Yeah.
Expand my consciousness.
Great. You know, I'd like to comment on that, both of those comments. What I've always started every math year with is art, geometric art. That kindles a lot of interest. What I realized, I'm not originally a teacher, I'm originally an engineer. I didn't have any concept of most of the stuff that I teach. When I have students start with a mandala, I find that, remember I said 1/3 are failing. That third thinks they are stupid. They're not. They're not gifted in mathematics, but they are generally very intelligent in music, art, sports. So I bring them in, kindling interest. And as we develop things, the consciousness expands, and it is amazing. Any other thoughts? Something I'd like to understand about mathematics? Okay, well, as we go on, if you have questions or ideas, please feel free to bring them in. What is mathematics? We'd probably all agree that mathematics is very logical. We use it for counting. We use it for adding up money. We're counting up how much we're going in debt each week. We've developed mathematics astronomically to understand how the length of the year works, to be able to predict the seasons, and to measure things. So we do need things like basic arithmetic, geometry, trigonometry. But why do we have abstract math like algebra and calculus? I've come up with 2 answers to that. One is that algebra and calculus are tools that we can use in higher math and science, but it's interesting to see students stumble with these in high school and university. What they do is it's an abstract development of the brain, working our brain muscles just like we lift weights to work our physical muscles. If we can figure out this algebra problem, I'm getting those synapses to fire, and maybe when I have real life problems, not mathematical, I can logically think through these things. I can open up my brain a little bit more to work through problems. So that's the conclusion I've come up with. But in all of this, we see, okay, there are logical reasons to understand mathematics.
You know that, of course, when you're in teaching, that the students always want justification for why they're learning algebra.
Exactly.
I think that what you're saying is a perfectly good reason, because it opens up abstract patterns that we might not otherwise have ever even explored. And you don't know when those patterns are going to be useful.
Exactly. I remember once that I was trying to work out some relationships in the classroom, and one of the teachers said to me, "Oh, you're such an engineer. You think you can just fix all these problems." And I was saying, well, but I can look at the problem from different aspects because I can work a problem from different aspects, and that's what algebra gives us. So it does widen our development. One of the important mathematicians in history was Pythagoras. Maybe you cringe, but remember his name for giving us the Pythagorean theorem, which relates to triangles. The interesting thing about our history of mathematics, for one, we don't necessarily teach it in school, which is a mistake, because again, there are multiple intelligences. One of them is historical. I can start talking about the historical person, Pythagoras, and people that are generally asleep in mathematics class are going to get interested. I can do a process of drawing the Pythagorean theorem, and the artists get interested. Next thing you know, a lot more people are sitting up in class participating. Pythagoras was fascinating. Actually, the Pythagorean theorem, for which he's credited, Pythagoras lived about 2,500 years ago, the Pythagorean theorem is known to have existed about 2,000 years before him, if not earlier. But Pythagoras was fascinating. He was Greek, and he lived, I think, about 700 BC, and he was educated, and he further was educated by the Egyptians. He went to Egypt, and he learned their temple science. He was probably initiated in the temple. So he goes there, and then the Babylonians invade and conquer Egypt. So one way or other, he goes off to Babylon. And not as a slave, interestingly enough, he studied there. So imagine, here's this original Renaissance man who knows Greek classical studies, knows Egyptian, knows Sumerian. What's he do? He goes and he makes a school. And in the school, he's talking about mathematics with number. How does he study number? He starts with the number 1. What does 1 represent? Me. What does 2 represent? You and me. What does 3 represent? Community, us. So he's looking at number totally different. He's looking at mathematics totally differently. People start coming to him. They sell all their possessions to the school, and they live as vegetarians. And those who are in the inner circle are called those who study all, mathematikoi. And those that didn't want to be vegetarians and sell everything and live in a toga the rest of their life, but wanted to know something, they sat on the outside. They weren't allowed to speak. They only listened. They were called acousmatics. Now, Pythagoras was fascinating. He was not only creating this school of wisdom or knowledge, he was trying to get society to be reformed. Now, he lived to a very old age. It's not clear if he died of natural causes or not, but after he died, none of his students died of natural causes. They were hunted, the school was closed, so they were very threatening. Mathematician philosophers, they were very threatening at those times because they were trying to reform society. The picture shows some interesting things. This picture is actually drawn, as you can probably tell, from the Middle Ages, showing them testing different bell sizes, glasses with different amounts of water in it. You could actually use these in math class to show how volume affects sound and tone. These are the kinds of things that Pythagoras taught for mathematics.
One thing you might do is, in the Pythagorean diagram, is instead of putting blank squares, put photographs because then you can announce that any object you see in the photograph has the same relationship. That is to say, the two smaller visions of it sum to be the larger vision of it. If you have a picture of a dog, the two smaller dogs equals the area of the larger dog. It's all proportional.
It is. I usually do this with what's called a 3, 4, 5 triangle, where you've got...
That's the Egyptian.
Exactly. You've got a 3 by 3 square, a 4 by 4 squared. 3 squared is 9, 4 squared is 16, and then they measure across the long side as 5 squared is 25. And the students, I had them do this by hand. And what's interesting, I teach middle and upper high school and university, and when I bring these things in visually, so many students say, wow, I finally get this. But what do we do in school? We say, okay, here's Pythagorean theorem. A squared plus b squared equals c squared. And then we give them decimal numbers, 1.2 on the side, 2.3. How can they solve that? They have to use the calculator. We've taught them nothing but how to push buttons on the calculator. And what do? They always ask me, Mr. Stang, is this correct? Okay, so they don't even have a relationship to the numbers to understand if it could possibly be correct or not. So there's all kinds of different ways we could do this much better. From the time of Pythagoras through the Roman Empire up to the Middle Ages, people thought that a basic education was called the trivium. It had to do with rhetoric, learning how to communicate. That was a basic education. A more advanced education, kind of like a master's degree, was called the quadrivium. It was about mathematics. And they said that you should study music for mathematics. Number, you should understand numbers, you should understand the earth, and you should understand the stars. What does that mean? The earth, geo comes from the Greek word for earth, Gaia, the mother goddess. Metrion, measure of the earth. Trigonometry, triangle measure, is how they measured, and did pretty well with this, measuring the distances to the stars, to the planets, not necessarily to the stars other than the sun, but to the planets, measuring the land around them. So this was taught all the way up into the Renaissance. Now, here comes the Renaissance. Great minds like Da Vinci, Copernicus. These people were educated as lawyers, doctors, priests. That was actually the third step then. After the quadrivium, they studied theology. Now imagine an education that's centered around math that focused on number and music, and then an advanced degree in religion. That, okay, granted, the Middle Ages, the church tended to dominate a lot of things, but science was not without God. So then comes the modern age where it's all specialization and separate from God, thanks to the French Revolution. I'm not going to say which one's better. It's just that I will say specialization is leaving us specialized and not really well developed into these other areas. Now, the thing that's nice about the classical ages and the Middle Ages is what we call sacred architecture, sacred geometry. I think probably a lot of people in the room realize what that is. And part of what that is could be represented by this. Now, I'd like to ask you, as I said earlier, for a little audience participation, could you please stand up? Okay, now, can you point on your own body where you think the center of your body is? Where do you think the center of your body is? Great, that's why I like doing this. Everybody points to their belly button.
Below.
A little below, okay. Now, put your hands to your side and feel that hard bone there. That's your hip bone. That is actually the center of your body. Please have a seat.
You mean the gravitational center?
Not the gravitational. Yeah, I didn't specify that on purpose. The measured midpoint of the body is right here. Now, this point of the body is proportional to phi, the golden mean, which is a key element underlying sacred geometry. That proportion, that's known as 1.618, is a whole topic on its own that I can spend 2 hours talking about. The key thing to understanding this is all of these symbols that are very familiar to us can be created using the phi proportion, or are consistent with the phi proportion. We find it on the piano keyboard. I've got a little example on the table back there. The yin and yang, the human body, special symbolism, Masonic symbolism especially. And this is a 5-petaled rose. That's a wild rose. All members of the rose family have a blossom like this. That means your apples, your pears, your plums, several berries. So these things are all related. And they're all related to what we just saw with our little demonstration. That if I measure, from here to the floor and compare that to my overall height, and if we do that in an average of this room, we get the phi proportion. If I take that same proportion and look at this generally measures 1 inch. This then is the phi proportion. This then is the phi proportion again. So essentially, if you're familiar with mathematics, this would be 1, this would be phi, this is phi times itself, phi squared, this is phi cubed. And these proportions exist all throughout the body. You can notice that, what is this? 1 and phi, and this is phi squared. 1 plus phi is phi squared. These are math concepts that I don't want to go into in great detail because I don't want to put everybody to sleep earlier than is your time. But generally, the thing that's fascinating about this stuff is that if the sun was right here, Mercury in its orbit around the sun would be right here. Venus would be here. Earth, Mars, asteroid belt, Jupiter, Saturn, etc. That's on an average.
How close of an estimation do you like to get before you actually call it phi?
What do you mean?
Well, most of these things, I've read a little bit about it, and it says that they've used examples like number of bees in the beehive and different ratios like that, and they say that it's not actually phi, it's a few decimals off. And so how close do you like to be before you actually consider it to be on average phi versus just a coincidence?
You know, yeah, that's why mathematicians get real funky about phi. If I try to bring phi into a room of mathematicians, some will start to leave the room. Others will say, "Oh, we're going to talk about God, aren't we?" Which is unfortunate, those kind of reactions. I'll give you an example. The Pyramid of Egypt, the Great Pyramid, measures 440 Egyptian cubits by 280, 28 by 44, 7 by 11. 7 by 11 is not an exact phi proportion, nor do the geometries of 7 and 11 create pi exactly. But the thing that's interesting is they create one by 99.6% and the other by 100.4%, which if you average those out, I mean, that's getting even closer. The universe and human endeavor seems to be built around a lot of very close approximations. As I said, if we take an average in this room, we'll get close to phi. Doesn't mean that we get exactly there. If I take an average of the planets, I'm not that close. I'm closer to phi than any other number. And then if I bring in Pluto, you know, Pluto, is it a planet or not? If I don't count Pluto, I'm even further from the norm. So is phi behind the nature of the cosmos? Personally, I believe it is. But nothing is exact in nature.
If it were, no creativity would be possible.
Well, questionable. Yeah, I mean, in mathematics is a study of patterns.
Look at
And
the keyboard there.
yeah,
It has to be shifted so that it actually matches, because if you go up a fifth and down a fourth, up a fifth, down a fourth, you miss the octave. You won't hit the octave. So you have to scrunch all the notes in a way, we call it a tempered scale.
Mm-hmm.
So none of the ratios are exact.
Of course not.
And when I say that, the octave is exact. It's the fourth, the third, and second that aren't exact because they have to be tempered.
I don't put the keyboard up here to show phi in the musical scale. What I do is I use it to show the Fibonacci sequence. One octave has 2 black keys, has 3 black keys, that makes 5 black keys, and then 8 white keys, making 13 keys altogether. Nothing in the universe, to my experience, is exact, but generally, roses, wild roses, and rose family fruits have a blossom that looks like this. Some might be larger, some might be smaller, but generally, if we look at these things, the patterns exist. Phi is an exact mathematical number. Nature, a lot of things come tremendously close. As I said, the spacing of the planets around the sun, the spacing in the human body, the 3 body segments in a bee, it exists in a lot of varied places. Spirals that form tornadoes, water spouts, spirals in the face, in the finger, spiral in the ear, in the hair. All of these things, they reflect upon phi. By the way, not just the planetary spacing, but if I look at the large planets, Jupiter and Saturn, if I put Jupiter here instead of the sun, its 4 major moons, spherical moons, will also be approximately in this spacing. Same with Saturn, except that instead of phi, 1 phi, it'll be 1 phi, phi cubed, phi to the 5th. But it's kind of like a harmonic. So it's generally pretty fascinating stuff.
Even the asteroids are harmonically distributed.
Well,
There are blank spaces.
yeah, that's interesting. What I find interesting is that the average of the asteroid belt is in the phi proportion, which shows that there probably was a planet there that somehow destroyed or didn't form properly. But there should have been something there, interestingly enough.
I'll mention that I don't believe that, but that's okay. I believe that all the large bodies have these rings, and all the large planets have now been observed to have rings. And the Saturn rings are also harmonically distributed.
Well, I'm not disagreeing with that.
Oh, no, I didn't say you were.
Okay.
I'm just talking like an idiot.
So the classical education was a lot more varied than what we have today. Today we value analytical but not sensory processes. The result of this, I'd like to read this, the result of this is that the creators of our technological world have little or no humanities in their education. And my experience, often have no humanity in their ability. When I was an engineer, I was required to take engineering law so I could keep from getting sued if something I designed killed somebody. But I was not required to take anything of a moral nature. What are we missing and why? It's interesting, in Europe, I have to teach the decimal system. And I ask my students, metric system. I ask my students, why do you like the decimal system? And they say, because it's easy. Okay, well, I like teaching people that can think more. One of the things that's nice in the United States and England is we still have 12-based counting. We have 12 inches in a foot, 3 feet in a yard, 5,280 feet in a mile. In decimal, in metric, everything's based on tens. With us, we have 1/16 of an inch, 1/8 of an inch. We have 2 cups in a pint, 2 pints in a quart, 4 quarts in a gallon. That's 16 cups in a gallon. All of these things make us think in 12s and 16s.
One of my biggest frustrations with our system, though, is why is there not exactly 5,280 feet in the mile?
Technically there is, but I was just reading an interesting book about different measuring systems. It was relating the megalithic yard to the meter. All of these things were developed out of people's best estimates at the time. And today we've got, satellite topography and all this laser stuff that we can measure it to the millionth of an inch. And so we have to correct things every now and then, correct the atomic clock so that we have a millionth of a second more each year for the next 2 years. 5280 works well enough and is really tied in well with not only 12 base counting, but 11, 13 base counting. We have all this different weird counting magically buried in the system that we use. Some of this stuff we have around us all the time. How many people have seen this before, the flower of life? Okay, we're pretty familiar with this. The thing is, I use that in my classes so the students start dividing a circle. As I said, we start with art. We start with mandalas. I get them to divide a circle by 6, by 12, by 4, by 8, and they find out, wow, I can do all of this by hand. And then subliminally, they're learning the key angles that they need for trigonometry. Now in school, what do we teach? We teach an angle, we give them the calculators, they take the sine and cosine of this stuff, and they come up with decimal answers. They write the decimal answers down. I did. And if they're with it at all, as I was, I recognize, oh, some of these numbers repeat themselves. But if we start using Mr. Pythagoras' theorem, we get familiar with things like square root of 2, square root of 3. What I find is I'll have students make things with their hands. This is actually kind of complex. I have them make cubes. I'll have them make little diamond things called octahedrons. And we work with the Pythagorean theorem with something physical. Again, I hardly let them use a calculator at all. In fact, almost not at all. Instead, I have them use a model that they make, and then I have them use the Pythagorean theorem. And what they find out is that, oh wow, radical 2, square root of 2, square root of 3. These exist in all these forms. It's not just random. I live in square and rectangular rooms, but these numbers that we study, these processes that we study, we can just use decimal numbers, which require a calculator, or we can do this stuff by hand, and we come up with square root of 2 and square root of 3. Ta-da! We come up with other fractions, 1/2. We come up with a whole value, 1. Isn't this exciting? I can take this sine function of 90 degrees and get 1. Everything else is a decimal number. I don't recognize these decimal numbers, but that's what my teacher tells me to do, so that's what I do. The thing about mathematics is we need to study math. We use math to study patterns. When we do that Pythagorean theorem, we can use whole number sides, but then if I try to figure out the angle, I get fractional angles, decimal angles. Should I care? Well, one basic Pythagorean triangle is the 5, 12, 13 triangle, and that is a roof pitch standard in the United States. It's easy to come up with. It's a nice slope for a roof to get the rain to go off the roof, and then all the houses look uniform because they've all got the same roof pitch. It's very standard Pythagorean formula. But the angles come out looking just like these decimal values here. There's no whole number relationship between angles and these math processes. But if we just get away from the technology a little bit and look at the numbers, look at the process, we realize, hey, there's a pattern here. The mathematics of 1, or the square root of 1, is the same. We learn in school 1 times something doesn't change anything. Something divided by 1 doesn't change anything. And that's all we do with it. But if I look at these processes here, I start finding patterns developing. When I start bringing this into the classroom, the students get really kind of excited about this stuff. As I've gone through math class, the unfortunate thing of modern education is we're teaching technology. We're teaching people that can use technology. It is not in anyone's interest to do this, in my opinion. What's happening is, instead of getting a sense of wonder about the stuff we're doing, we're just pushing buttons. As I've stepped away from doing that and have tried to think and get my students to think, a lot of the times we've discovered these things together. So it's not just exciting for me, it's been exciting for them. What I'm finding is really ancient symbols that we have around us aren't just random things. Maybe you recognize in the Star of David the flower of life. It's the same geometry. Flower of life is very soft and delicate, very feminine. This is a masculine form. Here we see the flower of life. This is really interesting, flower of life and the Star of David. This is called a sound pattern on a Chladni plate. Basically, and I've actually reproduced this, if you take a rigid plate and put sand on it and stroke it with a violin bow and get a tone in there, just a hum, the sand starts to dance. The sand or the beads or the salt that you put on there, it'll start to dance. And if the plate is round or if it's square, it dances in a different pattern. Now what's interesting is it's not a random pattern. It will form a star shape. This is one that's probably been done on a round plate. Now the interesting thing is on a flat plate, it looks like the Star of David. But sound isn't flat. The sound goes out into three-dimensional space. Sound goes, we learn that sound and light go in waves, but those waves interact with each other. The waves hit off the walls, they interact, they bounce into each other. And it's thought that the interference pattern created by that interaction three-dimensionally forms points called nodes, which would basically be like the points on the end of this. And so these nodes actually form in the basic forms known as the Platonic forms. So this is a two-dimensional image of what I think sound and light actually do three-dimensionally. And we see it in the same basic hexagonal form that we're using when we teach trigonometry. We see that we can make, with our hexagon, we can make different three-dimensional forms or different two-dimensional drawings that look three-dimensional. And actually, there have been some people that have done that throughout history. This image on the left was done by Da Vinci. What's interesting is I went and I drew something like this. I thought, as I thought many times, wow, I've developed this great new thing, this great new image, or this great new understanding. Go look on the internet and find out, okay, somebody found that out 2,000 years ago. But Da Vinci got into this, and also Salvador Dali. So some of the great artists of our time, other than my humble self, have also tried to work with geometrical forms, and it's because they've had an understanding of what we call sacred geometry.
What about Escher?
Of course, Escher, if you look at Escher's work, there's a lot of hexagonal stuff in there. So this stuff dates from about 1500s from a guy named Wolfgang Jamnitzer. And again, you may notice the hexagonal shape in this. So we can do a lot with that hexagonal picture. We can teach trigonometry. We can teach tremendous geometric art forms. Or we can look at nature as an example. Why are snowflakes six-sided? Does anybody know? Does anybody know why
It has
snowflakes?
something to do with the shape of the H2O molecule.
Which is?
2 hydrogens and 1 oxygen.
Okay, now what happens if I have an oxygen and 2 hydrogens are joined up to it? Do they come in from the sides?
They come at a certain specific angle.
Why is that? Why do they come at an angle?
Molecular geometry.
It's in the thank you. It's in the molecular geometry that the oxygen needs to fill 2 electrons, and it gets those from 2 hydrogens. But it already has some of its electrons filled. So it's kind of lopsided. The 2 hydrogens clump onto one side, and so we've got what's called a polar molecule. A little more positive on one end, a little more negative on the other. I probably have that opposite. A little more negative here, a little more positive here. Now because of that, water, when it solidifies into ice, it forms crystal structures, and they're not just cubic, they're hexagonal. That is the same reason why our microwave oven is able to cook our food, because that polar molecule, a microwave comes in here, positive, negative, and it hits the water molecule and it rotates it, positive, negative, against other molecules, and so they're rubbing each other, creating heat. And so the water in the food is what's cooking the food. That is the same reason why our heads get warm if we use our mobile phone, because the microwave from the mobile phone is going into the water molecules of the brain, tissue, and heating things up.
Actually, I think it's tetrahedral. The water molecule,
It's kind of, and I'm coming to that, it's kind of. Okay, now these other figures here are called radiolarans. They're single-cell organisms in the ocean. Now remember what I was saying, that sound and light, okay, forms these patterns. Now, you see the Star of David, but in 3D, that would actually be 3 points and then the top of a tetrahedron. Okay? Now, what I believe happens is that sound and light, traveling in waves, forming these nodes, actually create a matrix that single-cell life can form to, not necessarily, but can form to. But these are also basic mineral structures. Diamonds, natural diamonds, form in this octahedral shape. So this stuff all kind of comes from the same hexagonal structure. We can make these things by hand. We can cut out hexagonal patterns, make one little cut here, make one little cut here, start folding the thing around and making 3D forms from this stuff. That's a really nice process to go through. And then we have, related to this is what we call a tetrahedron. Okay, if I draw lines between each of these could be molecules or atoms, I'll get a 4-sided pyramid. Not a pyramid like in Egypt, but one with 4 sides. I'm actually showing 3 sides here, but this is a CH4 molecule, methane. It's a basic building block in a lot of things. Human fart. Sorry?
Including protein.
Okay.
You say that well, that's, never mind.
Well, it's also basically, I always tell my students, my teenagers, that when they fart, the methane molecules that they're releasing are in this form. So they're letting little tetrahedrons go off into space. This same basic math has been used for different symbols. The peace sign. We've got a lot of symbols around us that we normally use in everyday life, and we don't even realize that something like the peace sign is related to trigonometry, to the trigonometry that we learned in high school. Trigonometry that we fell asleep to in high school is directly related to the peace sign. And then we have another image of the sound wave called chematics, study of sound, study of light. This is 12-sided. And while on the subject of 12-sided, I'd like to return to this. Again, as I said, this is our flower of life, and I use this in class. I divide this to get students familiar with 30 degrees, 90 degrees. We can work this a little bit more to get 45 degrees. But does anybody recognize where else we could find this?
Lots of flowers.
Lots of flowers, yeah.
Lots of people do quilts to a pattern based on this.
Okay.
Glass.
Stained glass.
Pennsylvania Dutch symbols on buildings.
If you notice here, there are 6 axes, so there's actually 12 lines radiating out from the center. This is how we count time. 12 hours in a day, 12 hours times 2 in a day, 12 months in a year, 12 signs of the zodiac. All of this stuff, anybody here study astrology?
Yes.
Okay, a lot of people do. The science of astrology is directly related to the science of trigonometry. In astrology, what angles do we look for planetary alignments? Squares, 90 degrees. That's right here. What else? Trines. How many degrees is that? 120. All right. 120. 60 degrees is a sextile. 180 is opposition. Astrologers use the same angles that trigonometry students use.
I'd like to mention something there. Since the mathematics we've inherited from the past, trigonometry and spherical trigonometry was from its origin Ptolemy. And Ptolemy wrote 3 books, and he was an astrologer. And one of his books was on the astrology interpretations, where he said that we are impelled by the stars, not compelled. And his astronomy book, and one on geography, because you had to be able to know where the stars were at the place of birth at the time you were born.
Well, that's exactly right. One of his books was called the Tetrabiblos.
Called what?
Tetrabiblos.
It's a short book, but it's the one on astrology.
Yeah, and in it Ptolemy was another one of these guys that went to Egypt. Now the Egyptians didn't write any of this stuff down. So here came the Greeks. The Greeks wrote everything down. So Ptolemy goes into Egypt and studies their work and documented that in the Tetrabiblos.
Well, Socrates didn't write anything down.
No, there are several like that.
Well, right. I shouldn't
Anybody
speak.
write anything down.
Sometimes I speak too generally, but
Epictetus didn't write anything down either.
But anyway, the Ptolemy, what he was writing was things like this planet represents cold, this planet represents hot, this place on the earth is hot, this place is cold. So when a hot planet goes into the hot space, this is going to be hot weather. If the hot planet goes into the cold space, we'll have rainy weather. So he was actually also predicting predicting the weather with this. There are modern day astrologers that are doing the same thing.
By the way, in his Tetrabiblos, he recognized the Jews as maintaining their time by the lunar year, which makes Methuselah about 72 years old when he died, which is pretty old for a sheepherder.
Well, they may have actually lived that long at that time, depending on things. But there are other guys that.
Years, that's doubtful.
Well, there are other people that the Sumerians said that certain kings' reigns were 3,600 years. So, you got to look at those texts.
I think that we got to look at the translator and what language mistakes he made in it.
There are questions about times. When they say 3,600 years, were they using the word year to represent day, to represent month? A lot of people look at Plato's story of Atlantis when he says he learned from the Egyptians that Atlantis existed 9,000 years earlier. A lot of people like to say, no, that was months. 9,000 months earlier would have corresponded to Santorini exploding and wiping out Crete. The problem, though, is if we look at the text where Plato talks about Atlantis, Timaeus and Critias, one of those texts, he's more talking about basic geometric forms. And because of that, they're given the name the Platonic forms. Now, these forms have been known for a long time. Here's an example of them. These are hand-sized balls that were unearthed in Scotland, and they're in the basic Platonic shape. These things predate Plato by, I believe, 4,000 years. So these forms have been worked with for quite a long time. But the interesting thing about Plato, in his text, he's talking about the perfect shape being the tetrahedron, the octahedron, the cube, the hexahedron. But it's in the same text where he starts talking about Atlantis. Now, the story of Atlantis, he's talking about these gods and all the stuff they're doing. But actually, there's a lot of mathematics buried in that story. But one thing very interesting about the story is he's talking about Greece. And he says, the Greece that we know today is nothing like the Greece that existed 9,000 years ago, which for us is actually 11,500 years ago. He says, it was a land that was lush, and the plains, there were great plains where they were doing farming. And then the floods came, the floods that buried Atlantis, the floods also buried parts of Greece. And so that today, all we've got are these mountains that the rivers run right into the sea, which is not found anywhere else. Interestingly enough, if you look at an underwater map of Greece, the water around Greece is only about 40 feet deep, 50 feet deep, which during the Ice Age would have all been above water. So here's Plato talking about the war of gods and men that happened 9,000 years earlier, and a lot of people say it's not based on historical fact, and yet he is accurately describing the landscape of Greece that existed at that time. And then he goes on to explain geographically where Atlantis is or was. And again, if we look at the underwater area around the Azore Islands, it perfectly fits with his description. There's all kinds of stuff in Plato's write-ups about mathematics and some interesting things. And actually, I've written about this in my book. At some point, I should talk about that. On the back table, I do have copies of my book. I've researched this stuff for 12 years as a teacher. I've worked for 12 years as a teacher. And each year, I've meditated over the summer about what more I could bring into each class, how we could be more creative. And I've gone into the class and introduced this, and we've unpeeled that onion. Year by year, we've taken another layer off of it. And that book is the result of that, of work in the classroom and also research in the field. So I invite you to take a look at it, and you'll find documentation about these things I'm talking about Plato's Atlantis, about how to create mathematics, how to understand mathematics and the symbolism of mathematics in much more detail. This image here was created by Johannes Kepler. Interestingly enough, he taught in Prague, or actually he worked in Prague, and then he taught at a university in Linz, Austria. And he would have gone through the town that I live in Czech Republic to do that. So he's kind of known as a local boy. But he's used in this image the Platonic forms, the cube, the tetrahedron, and inside these smaller forms are the dodecahedron and icosahedron. And he said, based on his study of the planets, that the planets were spaced according to this model. And he was actually pretty close to this. Again, was it exact? No. But it's about 99% accurate. So we find all these little coincidences. And there's a guy that's written a book called The Little Book of Coincidences where he talks about this stuff. One example of that is right here. These are well, the one right here is a fractal. These are images that I have my students create. But interestingly enough, what this guy has discovered is if I look at, I believe this is, since it's 12, I'm going to say this is Earth. Something's not right about this, but he was saying that the relative spacing of Earth from the sun, if the sun was at the center of this inner circle would be Earth's orbit around the sun. This outer circle would be Jupiter's. Conversely, here, this eightfold image, the inner circle that touches tangentially inside the octagon, that could be Mercury's orbit, and then this external one would be Earth's. And it's, interestingly enough, that this is also the proportion of the planetary sizes, the smaller circle being Mercury's size and the larger circle being Earth's. So we can find some of this astronomy around us in the geometry that we can use in our classes. But we do have geometry in use all around us. The Native Americans used geometry in their medicine wheels, a mandala. The East used mandalas. The Christian church used mandalas in their stained glass windows. The Tibetan symbol of infinity. Seems kind of complex, but if we rotate it a little bit, it's really just an adapted square. If we look at it from this side, it's a lot easier to draw. A lot of different cultures have used geometry in their symbolism. It's the same geometry that we use in our trigonometry. Does anybody here know what Kabbalah is? Okay. The Kabbalah, notice again the hexagon in the Kabbalah symbol. And then extend it outward. This is all done off of the same imagery that we saw with the hexagon. So this symbolism that people use either for deep metaphysical studies or just as religious symbolism, in many ways is just based on very simple geometry that we can teach in our schools. Why we don't teach that in our school is a real shame. One thing we teach in school with trigonometry is the sine wave. And we say, okay, sound, light, oceans, waves travel in this pattern. But the only problem is this is on a two-dimensional image. What's interesting is that we need to realize that the wave is not going like this, but the wave is going out like a spiral, because things in nature go as spirals, not two-dimensionally necessarily, but as a spiral, a 3D wave. For example, like this spring. Okay, notice that this spring, if I rotated it sideways, I'd get a sine wave. Now, what's interesting in school is in grade school we teach basic stuff. We teach things like the moon goes around the earth in a circle. The earth goes around the sun in a circle. Nothing could be further from the truth. We go into high school and we start teaching, again, Kepler. We start saying, well, Kepler said that the earth goes around the sun in an oval, with the sun at what's called one of the nodes, one of the focal points. And again, nothing could be further from the truth, because the sun at that focal point is moving. So the earth is not going in a circle or an oval around the sun. The sun is moving. So the earth is actually spiraling in its path.
The earth's not spiraling around the sun, but it's circling relative to the sun. And if you're going to talk about the path, then don't you have to take in the galaxy's path? Maybe I'm being correct.
Well, no, I'm getting to that. Good. The first point is I'm trying to get you to realize that the Earth's motion is not circular or oval, that it's moving. Okay, but the fact is that the sun is not moving linearly. The sun is also moving about a central point in the galaxy, and so the Earth, if you see a slinky, how you can roll that around in a toroid, that would be even more indicative of the Earth's actual motion over thousands and thousands of years. Interestingly enough, if we look at the moon Does the moon go around the Earth in a circle or an oval? Absolutely not, because the Earth's moving. So what the moon is actually doing is moving this way in the same sinusoidal pattern. And that, interestingly enough, is reflected at Serpent Mound in Ohio. Now, I've been at Serpent Mound in Ohio, and I've been there at the solstice sunset in December and seen the solstice sunset go right along this line, right through that spiral. And it's documented that the solstice sunset in the summer goes along this line. And in between our 6 months that could be represented by the 6 paths of the moon going around the Earth. If that's the case, it's pretty interesting that the Native Americans realized this thing, that the moon's trajectory is more of a sinusoidal spiral than what we're teaching in school, this circle or this ellipse shape.
I know it's Indian rather than something left behind by Leif Erikson.
Well, you know, that's the question. What I have found, and I talk about this in my book, my book is a summary of 12 years of teaching and research, as I said. And so there's all these chapters on various things. You can open the book up to chapter 2, which I would not recommend you do. Chapter 2 talks primarily about things that I think we need to be emphasizing more in a high school classroom, and why. It comes from direct teaching experience. But there are other chapters that talk about things like, well, let's put the Serpent Mound, let's put the pyramids of Egypt and the Mayan world, let's put Stonehenge in a context together. What I've found is that a lot of these sites have amazing astronomical angular relationships. It's known that at Stonehenge, for example, that the sunrise maximum and the moonrise maximum are exactly 90 degrees apart. You have to do that at only a certain latitude to get that angle. That angle of latitude where Stonehenge is the same angle of slope of the Great Pyramid. And the angle that it's facing on the horizon is, again, that same angle. There's only one place you could build that on the Earth, and that's where Stonehenge is. The same thing occurs in the area of Serpent Mound. So that these people, these disparate cultures, were apparently looking for a same rather complex mathematical angle, which points me to the conclusion that there was a worldwide school of study of the stars, and these guys were able to mathematically make these connections from different places on the planet, and I think their schools must have been in conversation with each other. And most of that stuff relates to phi, the proportion I was saying found in the human body and the spacing of the planets. Now, phi is all around this form, the icosahedron, which is at the core of this, and the dodecahedron around it, as I document in the book. But I've made a further discovery, and I hope you can see this. The image on the left is a 5-pointed star. And you can see in the 5-pointed star that I can trace the spiral around it. That spiral is called a phi spiral. Well, I've done some interesting work with the 9-pointed star, and I've found that the 9-pointed star, I can also generate a spiral, very similar spiral. But even more fascinating is that all the tremendous mathematical stuff that is known about the phi proportion, there's a whole lot. There's a lot documented. There's a lot on the internet. I believe I've actually uncovered a few further things, and it's in my book. But when I look at the 9-pointed star and find that a spiral exists there that follows the phi pattern, has some tremendous mathematical relationships that follow the phi pattern, but is separate, it points to me as, what if phi, the golden mean, is only the start? What if in every star geometry, a 5-pointed, a 7-pointed, a 9, and 11-pointed geometry, there exist further proportions, further things to be discovered, further patterns? So that's part of what's fascinating to me about mathematics is
You've used the Greek letter psi.
I use the Greek letter psi because phi was used to represent 1.618. I have found that this number directly corresponds to everything we know about phi. It's not as magical as phi, but it's not bad. And because of that, I've assigned psi to it. Nobody's told me I can't do that, but but anyway, I've got things about that documented on my website, which is here, and there's my email address. If you'd ever have any questions or further interest in this stuff, you could look up more of this. But that pretty well takes care of everything that I've brought here. So if you've got questions.
I'm just unclear on what exactly the phi pattern is that you're saying.
Well, the phi pattern.
Is it like, what is it proportional to? The larger one is 1 point such and such times the smaller one?
Yeah, let me give you a diagram here. If I can find my phi diagram. As I said earlier, phi is an entire discussion on its own, as it rightly should be. But if I look at the 5-pointed star, for example, the phi proportion's all over this. And I can trace it in a 5-pointed star. I don't have everything shown here, but if the internal pentagon measures 1 on a side, the leg to the tip measures exactly phi. That's the phi proportion.
It's exactly phi times the inner one?
Exactly. So if this measures 2, this is 2 times phi. The two combined is 1 plus phi. Well, that's phi times itself. If I go across the whole leg, that's phi cubed, and then I can start adding up the segments, 1 plus 2 phi, and as I do that, I see that this proportion, which is generated by the Fibonacci sequence, if I multiply it by itself, I get a dual Fibonacci sequence generated out of that. Now the thing is, we could pick any two numbers, 300, 8 million, and we could add those numbers just like the numbers in the Fibonacci sequence, randomly generated numbers, and those numbers processed the same way we do the Fibonacci sequence, generate phi. If we take phi, which is the quantity 1 plus square root of 5, and divide that by 2, that is exactly the numerical value of phi. If we multiply that together to square it, we got to work with radical numbers and whole numbers. It's basically what's called a plus b quantity squared. We teach this in algebra. A plus b quantity squared is a squared plus b squared plus 2ab. And then we apply it. X plus 2 quantity squared. Well, what have we done? We've just taken two symbols in a formula, we've put new symbols in there, we've spit it out, and the students walk away saying, okay, well, I can do it, so what? If we apply it, again, remember, in school, what are we doing? We're giving the calculator. But if instead we apply real processes, they can generate and discover further fascinating things about the Fibonacci sequence and about phi. I won't go into detail with that because that's hours and hours of discussion, but it's all documented in my book. If you've got an interest in phi, you need to open up chapter 5. Any other questions?
Do you know how they originally, or how whoever came up with it originally discovered 1 plus phi equals phi squared? Like what particular steps they went through to figure that out?
I don't know what they went through. I discovered it myself in class. And what I was doing was we drew the star, and I was tracing around it, and I was adding the things up. We were using a calculator, and I, out of the corner of my eye, I saw the sequence developing. I was like, wow. And the students were like, we don't know what's going on, but our teacher's excited. We're excited. And as I said before, So, wow, I've made this great discovery, write it down thinking I'm super, do a little research on the net and find out, oh, well, this website's got it, this website's got it, this website's got it. What I'm finding as I go through this stuff time and again, I get on the net, I find out that Da Vinci found it. And I'm not saying I'm as great as Da Vinci. What I'm saying is that in our research, as we dig through this stuff, I guess you just find it. You just find it. So it's there for everybody to find. That's what's fascinating about it. So if we do geometric art, as I said, I was doing geometric art on a 9-fold star. Why? Because when we measure a circle and say it's 360 degrees, we can divide that by 3, by 4, by 6, by 8, and we get all these angles that we use in trigonometry, 30, 60, 90, and 45. If I divide by 5, okay, there come whole numbers, 5 times 72, 144. These aren't necessarily trigonometry angles that we use in trig, but they're all over phi. So what's left? Of all the numbers that divide into 360, 9 and 40 are left. So I said, well, I'd like to dig into this. How can I make a 9-pointed star with a compass? I can make everything else with a compass. I found out a lot of stuff, still can't do it. But then I started discovering this further geometry that follows phi. So, as we dig into it, as we peel the onion away, remember, as I said, I've done this for 12 years. Each year I dig in a little further and a little further. There's tremendous discovery. We can use the calculator as a tool to help find it, but instead what we're doing is we're giving the technology and education and is squashing it. Questions?
You were going to tell a story about your French student.
Right, I wanted to mention that. Thank you. I'll give you a great example. I've got a French student, had a French student. She came to me from France, and her grade report card, the math teacher had written "le catastrophique." Now, whether teachers are that blatant or not, a lot of people grow up thinking they're stupid. I'm just stupid at mathematics. I was just stupid at mathematics. And that's really unfortunate. Now, this girl is a gifted artist. I've worked with her. I've gotten criticized by inspectors from the Czech schooling system that I was spending too much time on her holding up the class. But today, she can pass a math class on her own. She's never done that in her life. She still fails math tests generally, but instead of getting 10%, she's getting 40%, 50%. That's pretty good improvement. And if I give a visual test, what's that mean? If I give a test with graphing, if I give a test of solving something that's got visual, not just formulas, but visual stuff, she can not only pass, she can get in the C range, and she can exceed about 40% of the class. So it's how we teach mathematics. It's not just this standardized process that we see going on. If we make it alive, we engage more of the intelligences in the classroom and have much better results. And she's one of them.
Yeah, you mentioned that you've taught for about 12 years.
Yeah.
And I wonder about your students who've gone on to advanced degrees. I mean, any stories to tell about them, what sort of mathematics they do, if they've made it to graduate school or past graduate school?
Unfortunately, today, I won't say most, a lot of students are not going to university because they don't need to. Give you an example. This student I had that was great, always, the one that everybody hated in class because he was the first to answer. He didn't go to university. Neither did his older brother. His older brother went, very intelligent guy, started an internet company, millionaire by the time he was 22. And he's gone to work for his brother. They charge 500 euros a web page. Now, I know that's $800. I know that it takes probably, 20 minutes to do one individual page of a website. So he creates websites and gets $800 per page of that. So that's pretty good, $800 for 20 hours work. I've got other students that have dropped out. And in the Czech Republic, what's popular is you go to Germany, buy a used car, bring it back to Czech, mark it up by $3,000 and sell it. Again, 1 day's work, $3,000. And this isn't just Europe. I had students like this in the United States before I left 8 years ago. The youth know there are paths to easy money, and they're bypassing advanced education. I have had youth that came to me and weren't sure what they wanted to do. They went through my classes and then started going after technical studies, architectural studies. So I have seen good results from that. The biggest thing is I've had my students come back after a couple of years and say, thanks, you know, I really got something out of your class. If you've seen Dead Poets Society, where the teacher's thrown out of the school and the students stand on top of the tables and as a salute, I've had students do that when I've retired from a school. I've had students stand up and applaud me. And I'm not getting into a big ego trip. They know what they've gotten in our classes together. And they can't articulate that so well because they're youth, but when I've taught adults at university, they've said, you know, why didn't I learn this in school? And that's why that's part of the title. Why didn't we learn this in school?
You said 12 years now. Is that here and there, or?
I taught 5 years in Denver and now 7 years in Czech Republic in the international scene. And probably for about the last 6 years, I've been teaching seminars for artists, teachers, homeschooling parents.
By the way, you know, Mark Twain say, don't let your schooling interfere with your education.
Mathematics you teach?
No. What I've tried to do is teach math, physics, and art simultaneously for my own benefit and for the students. Because what's happening in the schools? I'll give you 2 examples. Physics class, level 1. The students are starting to do scientific notation. Physics teacher says, oh, well, this should have been taught ages ago in mathematics. And it was. So briefly covers it, moves on. Tests the students. They all fail with scientific notation. And he says, why isn't this being taught? The math teacher has no idea because these guys aren't talking to each other. The math teacher has no idea that the students at this stage need to know scientific notation. And the high school math teacher is saying, that was taught in 6th grade. Why would I want to teach it now? Because now it's being applied. It's complete confusion. This is happening across the board. Physics teacher might be teaching something that requires a fairly complex algebraic manipulation, hasn't even been taught yet in mathematics. So the classes aren't being taught together, and then the science teachers are saying, oh my God, it's all the mathematics. They don't understand the mathematics. Well, but I don't have enough time to bother with that. Every science book, the first chapter is mathematics refresher. This is the second thing. Every book, the first chapter is mathematics refresher. They skip it. They all skip it and they say, I don't have time for this. I don't need to do it because the math teachers are doing it. The problem with that is the students need it. They need the refresher and they need it taught simultaneously with the math program. So there was one year, boy, my students sure had luck that year. I was asked to also teach chemistry. I taught chemistry, physics, math, and art. They couldn't get away from me. They had hours of me every day of the week. But I was able to understand where all the pieces fit and need to be taught. And most curriculum don't have any time for this. So the teachers are up there cramming this stuff, testing, filling out the paperwork that's saying the child's not left behind, and the child is being left behind, but all the squares are being filled in. What I have found is I take more time than the curriculum allows to do these things. The student gets more interested, and I spend less time trying to cram it in because they're doing their homework now. They're asking their partners how to do the stuff, so they've got study circles formed from this. So their buy-in is there. I don't have to keep telling them how to do it. They're asking questions how to do it, and they're asking people other than myself.
One thing that I heard you mentioned, at least alluded to, had to do with statistics, which is a specialized branch of mathematics, if you will.
Mm-hmm.
And most places, statistics does not get taught until, of course, you need to use it for whatever it is you're doing scientifically, or physics, chemistry, or what have you.
I think that's an important complaint. Because when you think about it intuitively, we use statistics every time we get up in the morning.
That's right. I use it every time I go to the supermarket, to
The-
my advantage.
The unfortunate thing with statistics is I have yet to find a way to make it as exciting as everything else I've done. For
Try
myself,
Tukey.
what?
Try Tukey, because he worked more with finding the hypotheses instead of hypothesis testing.
Mm-hmm.
And I think that the finding the hypothesis is more directly related to the kinds of things, the discovery is what you seem to be emphasizing here.
Mm-hmm.
And Tukey is one of the great ones for showing, he was a Princeton statistician, he invented all kinds of new techniques for how to find things in data.
Well, statistics are where everything's at now. If you want to get a government grant to do any research, you're going to have to provide statistics to get it, to justify it, whether it's math, whether it's biology, plant studies. Statistics is almost everything. But what I find unfortunate is it's very dry, whereas this stuff is very alive.
I'd say it's very dry in the ordinary way of teaching.
In the ordinary
If
way.
they use a few of the techniques you're using over here, it'd be a little more wet.
I'm only saying that I haven't found it yet for statistics because I don't like statistics. But it wasn't one of the 4 classical math studies, so it doesn't exist for me.
Well, I've got a book that will really help you called How to Lie with Statistics.
Well, that's a great one.
And it's like you read this, and it's like you have your students going out looking at the advertising, looking at the newspapers, you know, how they portray the graphs, how they cut the bottom off, all this kind of stuff that you find in the stock market, and it makes statistics alive because you realize how much you get manipulated by people who know how statistics work and then misuse it. And
Yeah.
They really get insight into it.
yeah.
That lying is only a small fraction of the whole.
Any other questions or comments?
Well, this afternoon you mentioned you'd gone to the big math conference in Wisconsin.
Mm-hmm.
And I just wondered about your impressions. I think this thing goes on for 4 or 5 days. It seems a huge, huge deal.
It is a huge deal, and they said it's gotten huger every year.
You know, that forces people to specialize.
Well, it does. It does.
So how do you go to all the events?
How do I go, or
No,
how
not
does somebody
you
go?
in particular, but anybody, you know, you generally.
Well, the general impression I had was it was geared towards academia. A lot of the vendors there were selling. Well, you know, this is what modern education is today. A lot of the vendors there were selling their textbooks that are very expensive, hoping to get schools to buy big gobs of textbooks, or else it was all techno. Techno. I looked once at a software program, algebra. How to have your student do much better at algebra. I started going through it. It was the exact same as a textbook. We don't need to be burning out our eyesight or our children's eyesight on a computer screen when they can still be touchy-feely on a book getting the exact same stuff. And it's a lot easier to go through. The techno is absolutely overemphasized, and it's all going that way. And you know, this idea that, well, we've got to have our children be more competitive in the techno world. I'm an engineer. I've learned dozens of programs as an adult. I've taught dozens of programs to adults. I've tried teaching them to children. The brain is not developed to use the computer as a tool. It uses it as a toy. So our children, you know, I've seen it at school. They're not playing outside anymore. They're playing on the computer or watching somebody else playing. They're more sedentary. You know, we've got great stories of wonder stories of the child that did this or that, the child that doesn't go to university but starts making millions on the internet. I feel sorry for this guy. This guy in particular, genius, and there he is going for quick, great cash. But he has, sorry?
Gates did it.
Gates, yeah. Gates is making billions off of giving children computers in the school, but it's not really a gift. When you look at what's behind this, when you look at one of the key ingredients of all the electronics, the computer, the mobile phones, the toys, the MP3s, it's called coltan. Find out about coltan on the internet. It's generally found in the Congo, and it's at the root of the Congolese civil war right now, where child soldiers are killing other child soldiers so that our children can have this key ingredient. It's horrific, the stuff that's going on with this. People like Bill Gates are making billions out of this, and other people, one of them's great, it's called the Alliance for Childhood. You can look on their website. They're coming out against computers and technology and education, and they're giving great examples. They've got a book, it's a free book on the internet, and a lot of doctorates have signed on to this thing saying, we need to turn this around. We need to completely look at education differently. The Pythagorean theorem today is being taught with decimal numbers. I have to have a calculator to solve that. My students don't. They've got a much better understanding of the Pythagorean theorem. They're working with real numbers, and they've got the excitement of discovery, which the calculator never gives.
I might mention that when the monks got printed books that scared them to death, they thought that the books would replace them as teachers.
Mm-hmm. Well, one day, one of my students was saying, he was pointing at the computer screen saying, "Mr. Stang, one of these days, you're going to be replaced by that." And I said, "Johnny, one of these days, so are you."
I definitely agree with what you're saying about a lot of technology starting to be more emphasized and the calculator taking away from a lot of experience that one can gain through personal discovery.
Mm-hmm.
But I also know through personal experience that I'm actually much better at math, and I'm actually going for a math degree right now, partially because of a computer I had use of. Because when I was learning the mathematics, I learned basic programming languages, and I started writing programs to see graphical effects based on the mathematics. And so that allowed me to have a lot of discovery because I could see the math actually working with, like say, a ball moving across the screen or two balls colliding together with physics. And so that made it alive for me. And so in that case, the computer actually helped a lot with bringing me into mathematics.
You know, as a tool, okay, am I saying don't bring the computer into the school? No. What I'm saying is that for younger ages, the teacher guides the work through the computer. Do you sit a 7-year-old at the internet and say, okay, find out about the Great Pyramids? No, because you know, most of the stuff's written by adults. It's way too advanced for the child. And if he doesn't image search on the pyramids, I promise you, from experience, he will find pornography with that, and countless advertisements. So, are there these cases? Yes. One of the unfortunate things, and I do say unfortunate, is that teenage boys are going at this stuff like gangbusters. Okay, can we justify it? Sure. But as a teenage boy who went at this stuff, I realize now as an adult, I really wish I'd have spent that time outside playing with my friends, developing a musical hobby. I'm seeing teenage boys particularly losing great portions of their lives because the electronics are a big drug for young men. So keep that in mind.
I see the computer as potentially a wonderful tool for helping to develop the brain. But unfortunately, it usually gets used as a substitute for the brain. They did an experiment with calculators where they had a whole class and they handed out calculators and gave them a whole bunch of problems to solve. And the calculators gave wrong answers. And they wanted to see, well, if you do this, it's like how many would actually look at these things and would trust their own judgment because they had them, versus the calculators. And only a very small percentage would go against the calculator. The calculator gave them the answer, therefore the calculator must have it right, and whatever they did, they must have made a mistake when they did their manual calculation.
I unfortunately see that all the time. The technology is trusted more than our own
well, it
thinking.
Goes to the idea of going back to the Bible, to sell your birthright for a mess of pottage. it's like we have these incredible capacities, and instead of using these tools, these incredible tools like with biofeedback and whatever else to help us develop these capacities, we use them as a replacement for them.
Mm-hmm.
And then if something goes wrong, like the calculator gives you wrong answers, it's like you just sit there, you push the button, you get the answer, and you just accept it.
Yep. Technology has its place, but classic education is where it's at for me. Well, thanks for coming out. So I really appreciate the interest.
Thanks for coming.
Yeah. Well.
RVML Resource Center is a volunteer-operated federal 501c3 tax-exempt nonprofit organization. RVML is dedicated to providing easy access to a comprehensive collection of information on a variety of metaphysical, spiritual, and personal development subjects. RVML accepts and appreciates all donations. Material and monetary contributions are fully tax-deductible. This recording is not copyrighted, and permission is granted to broadcast, exhibit, or duplicate all or part of this program for non-commercial educational purposes. This live presentation was organized and presented by the Rogue Valley Metaphysical Library and Event Center. For more information, please visit rvml.org.